My name is Doug, and you can hear me in the back okay? People in the back row, okay? So, a couple of things to start off. First of all, when you start doing the tutorial, like when you open up your laptops and you start it up and you start up Firefox, you should come up to this page. And so even though I know that you have a physical copy of the lecture slides, there are also slides, the slides are also on here. So if you click, say, on this one where it says Analyzing the Individual Subject, you will bring up my slides. So if you want to follow the slides from your laptop, then that's possible, or you can follow them from your book, or you can just chill out and look at the slides at the front of the room, like people used to do. Okay, so now what I'm going to be talking about is doing the first analysis with FreeSurfer. So there are lots of things that you can do with FreeSurfer, including DTI, FRI, and pet analysis, and Campbell subfields, and all this kind of stuff. But all of it is going to be based upon the assumption that you have taken your input T1 image and run it all the way through FreeSurfer. And so, if you want to go off and do group thickness maps or whatever, this is something that you will always have to do no matter what aspect of FreeSurfer you're going to be using. So I have an overview of this slide here as this kind of clock figure. And at the center of the clock is this T1 weighted image, which is the input to FreeSurfer. And on the right side, between 12 o'clock and 6 o'clock, are the volume-based analysis that FreeSurfer has to go through. And on the left side of the clock, from 6 to 12, is the surface-based analysis. And so this talk is all about how to go from 12 o'clock all the way back around and complete your entire first level analysis in which you're going to characterize all of the anatomy for an individual subject. So as Bruce mentioned, you start with the T1 weighted image. So for those of you who don't know, a T1 weighted means that white matter is brighter than gray matter, which is brighter than CSF. So it kind of looks like a brain if you were to get it up, but that's only by chance of MR physics. There are constraints on the quality of the image that you need to collect. So it needs to be somewhere around 1 millimeter cubed, or certainly no more than 1.5 millimeters. So this eliminates a lot of clinical scans, because radiologists like to look at scans with very thick slices, so like 3-4 millimeters thick. So that's going to fail inside of FreeSurfer. As Bruce just mentioned, you have to have full brain coverage to run this through the FreeSurfer pipeline. Although if you have multimodal images that are not full brain, that's totally fine. But for this T1 weighted image, it always has to be full brain coverage. Usually one acquisition is okay, but if you have, say, high acceleration, then maybe you want two. Typically on a Siemens platform, you would collect something called an MP Rage. Or on a GE platform, you would collect something called an SPG Guard. It works for 1.5T and 3T. We've also run it on 1T scans, and it works pretty well. 7T scans, it also works pretty well, but there are some problems with it. Subject age probably needs to be greater than 5 years old, or maybe 3 years old, something like that, because when children are very young, the gray matter is actually brighter than white matter, because white matter is not myelinated. Until white matter myelinates, it's going to fail inside of FreeSurfer.
Are there any manipulations you can make to do like fetal or early life scans?
Are there any manipulations you can make to do fetal or early life scans? I think is Lila around? Lila, are you going to talk about that? Okay. Yeah. So Lila's going to talk about that later on. The brain has no major. Oh, sorry. Go ahead. Oh, sorry, I did miss that. Why is high resolution worse? For two reasons. One, when you collect something that's very high resolution, you lose signal to noise in each individual voxel, so the entire image basically becomes noisier. The other reason is that there's a lot of anatomical details that are in there that we are not modeling. So you can see fluctuations in the intensity of white matter. and sometimes that will end up getting picked up in FreeSurfer. So the brain has no major problems to it, so if somebody's had brain surgery, you have lobes that are removed, you can run it on FreeSurfer, but in the areas where the lobe has been removed, it's probably going to create problems, as will things like tumors also create problems. Non-human primates are possible, so there's a sub-community of FreeSurfer analysis people who are doing monkey, and I think I've even heard dogs. Like several different types of analyses are, with different species are possible, but it's totally geared towards the normal, semi-normal human brain. Okay, so we have all of those cool things that Bruce just described to you. And so how do we get those? So we start off with this command called ReconAll, and I know that Allison mentioned that in the FreeSurfer jargon talk. So this is the fully or nearly fully automated reconstruction. And so by reconstruction here we mean the anatomical analysis of the brain. This is a slightly historical nomenclature to call it a reconstruction, because this is what we think of in terms of reconstructing the actual cortical surface. But this is going to go through and run through every analysis that FreeSurfer has for the individual subject. And this should not be confused with a case-based reconstruction. So if you don't know what a case-based reconstruction is, then I've probably just confused you even more. So case-based reconstruction is when you collect data on the scanner, you're not actually collecting images, you're collecting a frequency spectrum. And then when you do when you convert that into an image, that's called a case-based reconstruction. So this is not a case-based reconstruction. This is simply an anatomical analysis. And if you were here for the Linux tutorial earlier this morning, you saw that FreeSurfer is not GUI-based. So what that means is that you have to open up a shell. So if you're not familiar with Linux or you don't use it all that much, if you're familiar with Windows, you're familiar with DOS, you remember how you can open up a DOS window and you actually hit keys on the keyboard to spell things out and you hit return, and then something happens. And rather than going and clicking, pointing and clicking and stuff. So FreeSurfer is kind of DOS-based, if you want to look at it that way. Which means that you're actually sitting down at you're opening up a terminal window and you're typing commands. And the one command that you really, really need to know is this command called recon-all. So you would sit down at the terminal, you'd open your computer, you'd open up a terminal and you type recon-all -I, and you give it file.dcm, and I'll explain what all these different flags are, -subject var -all, and it goes off and it runs the entire reconstruction. And it does, so mostly what I'm going to be talking about today is what this command is doing, and it's going to take 6 hours to 20 hours, depending upon various things for it to run. And so what I'm going to talk about for the rest of the talk is what happens when you run this command. Because even though it's all fully automated and that you might have to get inside of it to be able to fix problems, and also we cannot predict exactly what it is that you're going to need FreeSurfer for. So as part of your education and learning how to use FreeSurfer, what we'll do is tell you everything that's going on, well, a lot of things that are going on inside of the ReconAll command, whatever the output that it produces, so that you'll be able to get what you need out of it. As I mentioned before, there's a volume-based stream, which are these basically these 4 items here on the right side, and then a surface-based stream, which are the items on the left side. And so it runs the volume-based stream first, and then it splits and does the surface-based stream. So this ReconAll command has 3 options that I have listed here, although there are a lot more to it. The first one is -I, which is and the argument to that flag, so that's a -I flag, and the argument to the flag is file.dcm. And that's supposed to represent a DICOM file. So when you go and you collect data on the scanner, it's going and you get, say, a CD, that CD is going to have a whole bunch of files on it, and those files are called DICOM files. And this is what every scanner in the world is going to give you information So this is a medical imaging format. And it's not particularly useful when you go actually to do data analysis. But this is what the scanner gives you. And so if you collect, say, a T1 weighted image, it's probably going to have something like 180 different files that are associated with that image. So if you have 180 different slices, it'll have 180 different files. And so all of those files collectively are called a series. And so when you run ReconAll, you just need to get one of those files from that series, and it will find the other 179 of them. And it will take that information and use that as input to ReconAll. If you happen to have two series, so if you've collected, say, two MP ranges, two T1 weighted images, you can give it a -I and give it a file 1.dcm, which would be a file from the first DICOM series, and -I file 2.dcm, which is a file from the second DICOM series. And it'll go off and it will find all of those, and it will convert it into a format more amenable to analysis. You can also use Nifty as input as well as several other different formats. It's best if you start with DICOM because we know that all the information about, say, which side is left and which side is right is correct in the DICOM. And of course, when you're doing brain image analysis, you want to make sure that you know which side is left and you know which side is right. Nifty has that information in it as well, assuming that it was transferred correctly from the DICOM into the Nifty. We really recommend that you not use Analyze format because that left-right information is not natively inside of Analyze. Okay, so that's the input file. The second flag is -subject, and the argument to this flag is called BERT. And the BERT, whatever the argument is to the -subject flag, is going to be the name of the subject, or also called the subject ID. And so what FreeSurfer is going to do is it's going to go out and create a directory, a folder, and it's going to do all of its analysis inside of this folder. And I'll go into great detail about what's inside of the folder. And so, but it has to have a place to put the analysis. And one of the things that makes it fully automated is that it has a place to put the analysis, calls things, files, certain names. So when it's going, after it's done with one stage in the process, and it runs the next stage, and the first stage has stored files in a certain way with a certain naming convention, and so the next stage knows where to get that information from. And so, so that's why it's important that you understand what this directory structure is going to be. So in this case, I've named my subject BERT, which is one of the subjects you will work with. And this BERT folder is going to go into a particular place in your file system called subjects dir. So if you see it here, this it has a $sign in front, and it's all capital subjects dir. And this is something that Renza went over during the Linux tutorial, but just as a reminder, this is an environment variable. So if you're used to using something like Windows or Mac, and say that you add a printer onto it. So a printer becomes part of your environment. And so what that means is that any program that you're writing on your computer knows what your printer is. So you install your printer and you run Microsoft Word and you print something from Word, or you print something from Safari, or you print something from PowerPoint. Every program on your computer now knows what this printer is because it's become part of your environment. And so it's the same thing with this subjects dir variable. It's something that gets set and it becomes part of, it's configured into your environment. And so every FreeSurfer program knows where the subjects dir is. And so you can think of it as the root of a tree, and then everything, all the subroots underneath that tree are where all of your FreeSurfer data will be stored.
Do you have to reset your environmental variables for each new terminal window?
You have to reset your environment variables for each new terminal window. The answer is usually no, because you can basically set this up to have it run automatically, essentially, every time you open up a new terminal. Although when you do the tutorials, it's going to tell you to reset it every time, but that's not necessary. But you might want more than one subject stir. So if you're doing multiple studies and you want you may want to separate them into different subject directories, and in that case, you will have to set them manually. The last flag is -all, and that tells it to do everything, which might sound a little bit redundant with recon -all. You would think it would just do everything based on its name. But we can also divide things up. So as you start to analyze your data, and you go in and you find a place where FreeSurfer has failed, and you make some modifications to it, and then you rerun it. It could take 10 hours, maybe 20 hours, maybe as low as 6 hours, depending upon the power of your computer to run. So this is going to go off, and it's going to do all of these things. So upon completion, as I said before, it's going to create this directory structure. And so again, it's going to put everything into this subject stir folder under whatever subject name you happen to give it. So we have BERT here. And if you were to look inside of this folder, you would see a whole bunch of subfolders, and I'll only go through 5 of them here. There's scripts, there's MRI, surf, label, and stats. And MRI is going to be where all of the volume results are going to go, and surf and label are where all the surface statistics are going to go. And then we have some table stats that are going to go into the stats folder. So under the scripts folder, if you look in there, you'll see something called ReconAll.log, and that's going to have all of the terminal output. So when you run ReconAll, it's going to start spitting stuff to the terminal, and then when it finishes in 10 hours, it's going to have a huge amount that it's going to send to the terminal, and that information is potentially useful in terms of trying to debug what's going on, or to see exactly what happened during an analysis. And so it's important that you know what this ReconAll log file is and where it is, because if something fails, then this is the single most useful element that you can send to us to help you debug the problem. At the end, it should hopefully say something like ReconAll finished without error, and it gives you the time that it finished at. Just because it says it finished without error does not mean that everything went okay. So you need to So you'll need to actually go through and take a look at your output to make sure it looks okay. We're going to go over that this afternoon. So upon completion, in addition to having the scripts directory, you'll have this MRI folder. And in that, you'll see a whole bunch of different files. And they'll all end with .mgz. So this is FreeSurfer specific format that's been around for 15 or 20 years or so. Way predates Nifty format. So this has a lot of information. It's like a Nifty file or an analyzed file. It has pixel data in it, and it also has information about geometry as well as some other things. So you'll see, if you look at these things, you would see all kinds of different files in here. The raw average.mgz, reach.mgz, t1.mgz, brainmass.mgz, wm.mgz, asig.mgz, and each one of these is, of course, a different output from FreeSurfer. So there's probably 10 or 15 different these volumes in there. And this is the output of the volume-based stream, which I'll go through. So there's a couple of quirks to FreeSurfer. So this raw average.mgz is, if you parse the name, it means raw average. So this is If you have multiple inputs, so if you collect multiple T1s on a given subject, it will motion correct those two together and compute the average of them. So that's what the raw average is. If you only have one input, then your raw average is just whatever your input is, exactly as it came off the scanner. Nothing has been done to any of the pixels or anything like that. Everything else will have been created in this, what we call conformed space, which is 1 millimeter isotropic 256 cubed. And this is a little bit, again, historical for FreeSurfer. So if your data started as, say, 1 millimeter by 1 millimeter by 1.1 millimeter, 256 columns and rows and 128 slices, then that's what your raw average would look like. And so the first step that FreeSurfer is going to do is it's going to take it and conform it so that it's 1 millimeter isotropic, 256 cubed, in a coronal slice format. And so that's going to be called the orig.mgz. And orig originally meant original, which would make you think that it was the first thing in the pipeline. But that's a little bit of a historical fluke as well. So orig is really just the initial conformed image at this point. So we refer to this as the anatomical space or the conformed space. And everything that FreeSurfer produces is going to be in this particular space. So all the surfaces, all of the automatic segmentations are going to be in this conformed space. So we have a native anatomical space and we have the conformed space or the FreeSurfer space or the anatomical space. And it's pretty easy to go back and forth between those two. So the next thing that FreeSurfer does is it runs through the surface-based stream once it's finished with the volume-based. And I'll go into more detail about what each one of these things is. And then what you would see in the surf folder, surf stands for surface, are all these things like lh.orig and rh.orig and lh.white and rh.white. And if you see an lh.something or an rh.something, it means it's a left hemisphere surface-based file or a right hemisphere surface-based file. And so these are different surfaces that will generate the orig, the white, the peel, the inflated, and the sphere. Mostly you're going to be interested in the white, the peel, and the inflated, and the sphere and the orig aren't particularly all that interesting. The next thing that FreeSurfer does is creates anatomical labels. So this is something that Bruce already went through. We have a desiccant atlas, desiccant Kiliani atlas, and a Destrio atlas, and they are slightly different. And so these are labels that are applied to each individual subject. So there's subject-specific definitions of, say, superior temporal gyrus or precentral sulcus or whatever. And then finally you have a statistics folder in which you're going to have all of these text files. And these text files are going to have things like the area of superior temporal gyrus, the volume of superior temporal gyrus, the average thickness in superior temporal gyrus, and all of those for every other label that we have. You'll also have volume-based labels as well, volume-based statistics. So what's the volume of hippocampus, what's the volume of amygdala, and then you can go off and do an ROI analysis as Bruce described in the previous talk, looking at the size of ventricles, for example. So these stat files are just simply little text files. There's also a Talairac transform that gets computed along the way, and that's stored under the MRI transforms folder, something called Talairac.xfm. And this is just a text file with a matrix inside of it. So the original data is not transformed into Talairac space. Everything is kept in the native space. So if you have a volume of hippocampus, that's the volume of hippocampus for that particular subject in the native anatomical space. And so everything that you see inside of FreeSurfer is native anatomical. We compute the Talairac transform as a way to be able to report Talairac coordinates. But for the most part, it's not used really all that much. Okay, so I said, if you think back to my little clock diagram, you had 4 items on the left and 4 or 5 items on the right. And so the 4 items on the right side of the clock are the volume-based stream. Those on the left side of the clock are the surface-based stream. So what I'll do is go through what these 4 items are on the volume-based stream for 2 reasons. One is so that you know something about what FreeSurfer is doing. And then the second reason is that there are certain failure modes that you have to be aware of. And Allison will talk more about that in her talk on failure modes this afternoon. So one of the first things that FreeSurfer will do is something called intensity bias correction, or also called intensity normalization. So these 2 I'll use interchangeably. And so what happens is that when you scan somebody, the brightness is not uniform across the image. So if you were to take just like a tube of water and scan that tube of water, you would see that on the image, like one side might look brighter than the other side does. And so the reason for that is varied and it's really complicated. It often has to do with the number of coils you have. And for example, the person, when they're laying with their head back into the scanners, the back of their head is going to be closer to coils than the front of their head will be. Usually you try to put some padding in it, but oftentimes the person's head is in there asymmetrically, and that's going to cause parts of the image to be brighter on one side of the head, say, and then in the other side of the head. And this is the example, or this is what's happening with this particular example, where you look at this grayscale image, and your eye is really, really good at removing these types of gradients. And so it's really difficult to see that the right side of the image is actually much darker than the left side of the image. And in fact, on the left side of the image, gray matter is as bright as white matter is on the right side of the image. And if you're trying to segment an image into, say, gray matter or white matter, this is just a killer. Because you would look at something in a certain intensity range and say, okay, that's gray matter. But it's gray matter on one side of the image, but white matter on the other side of the image. And so that can be very problematic. And so one of the first things that we do is to attempt to remove what this bias is. And so the input to this is the orig.mgz, and then it creates something called t1.mgz. And so this is also a place where FreeSurfer can fail if it can't quite figure out what this particular bias field is, and they're trying to remove it. One of the next steps, oh, sorry, go ahead.
So you say more coils, this works, so do you recommend 12 channel over 32 channel?
Would I recommend 12 channel over 32 channel? I would not, because the 32 channel is going to give you a lot more signal to noise. And in general, these bias fields are something that we fix pretty well. So I would definitely not try to dump down your scan to make it work better in FreeSurfer. You definitely always collect the best scan you can.
So this T1MGZ is the homogeneity corrected?
This T1 is the homogeneity corrected image. Yeah, it's actually a little bit even more severe than that. It's actually a pre-segmentation, where if you look in the T1 at MGZ, you're going to see that values inside of white matter are mostly going to be 110, and it's going to be flat, so you will lose any variation. There's another file in there called nu.mgz, which is a softer version of this intensity segmentation.
Acquiring a B0 or B1 field map help?
Sorry, was that?
Would acquiring a B0 or B1 field map help?
Would acquiring a B0 or B1 field map help? B0 will not help. B1 is only part of the problem. So you have coil profiles which cause intensity variation. You have B1. B1 at certainly 1.5T is probably not going to help at all because you don't see very much variation. At 3T, maybe it helps.
It's a bigger deal at 7T where you have dielectric effects, but it's hard because dielectric effects are so bad that you get pile up. So we have. So the other problem is that the B1, there's no closed form solution for what an MP range looks like. It's not a steady state sequence. So for an SPGR, you have a steady state sequence, and it's easy to kind of stick a B1 map into it and correct for things. But for an MP range, it's hard because the MP range depends on the anatomy because it has this kind of strange frequency filter in it. So yes, we have some tools for incorporating B1 maps that have made things somewhat better at 7T if you're doing Flash or SPGR, but not really for MP range. I would also follow up with the coil question, that they're like 8-channel coils that are really, really hard to analyze because they don't have coverage near the vertex. So you get this whole region at the top of the head where you have very little signal. And so the larger N arrays are typically better for that kind of thing. So it really depends on coil geometry. It's not just coil count. You know, like the 32 channels are really good. The 12-channel Siemens is actually pretty good as well. The 8-channel arrays are usually awful, except if you happen to have a better distribution of coils.
The next step is skull stripping. So it's actually not a great name for it because it's actually removing everything that's outside of the brain. So it's the skull, the eyes, the neck, and the dura. And even though we say it's skull stripping, you cannot actually see the skull on an MR image. It's actually very, very dark because bone is dark in an MRI. What you're really seeing is basically the scalp. But it's actually just trying to remove everything that is not part of the brain. And so this can sometimes also fail by removing too much or not removing enough, and that might require manual intervention. When it's done, it creates a brainmask.mgz file. So it takes the t1.mgz as input and creates a brainmask.mgz. Yeah?
I've heard skull stripped a few times and had it leave, a little cap of skull in some places. Registration seemed to be good otherwise, and so I've always moved forward with those. But is there any problem if it doesn't entirely strip the skull?
Is there any problem if it does not entirely strip the skull? Can I defer that question until this afternoon when we'll go through the failure modes? One of the next steps is the automatic labeling. And so this is, as Bruce mentioned, it labels all the subcortical gray matter structures. It labels cerebral white matter, it labels cerebellum gray matter, white matter, and then it also labels cortex. And so while the subcortical aspects of it are accurate, the cortical one is not necessarily all that accurate. And so this is obviously useful in its own right because you can compute, say, volume of the hippocampus. But it's also useful when we go to take the further step of trying to isolate where the cortical surface is and actually build a surface-based model. So this is nice because it will allow us to fill in, to know where, say, ventricles are, and to know basically where white matter is. And we can use this as essentially a starting point for building the surfaces. The next step is something called white matter segmentation. And the output of this is called wm.mgz. And there's a temptation to look at this and say, okay, this is the WM means white matter, and so this must mean a white matter segmentation where every voxel is non-zero if it's white matter, or 0 if it's not white matter. And that's not quite what this volume happens to be. As you can see inside of here that ventricles are filled in there, and you have the putamen that's filled in there, and hippocampus might be filled in. So what this is basically subcortical mass. Everything that is inside of cortex is non-zero here, otherwise it's 0. And this is going to be the starting off point for creating the first surfaces, which is done here. So this is immediately after this is surface extraction. So the way the surfaces are going to be built is that we take this wm.mgz file and we'll essentially like glue the surface around it. If you think of maybe like taking this subcortical mass and dipping it in chocolate and bringing it out, it would be completely covered by chocolate, which would then harden around it and be very delicious. So this is the transition from the volume-based stream to the surface-based stream. So the volume-based stream, we had intensity normalization to remove bias fields. We had skull stripping. We had subcortical labeling. And then we had this white matter segmentation. So those are the four steps for the volume-based processing. All of that is stored under the MRI folder in your subject stir. And now we're stepping into this brave new world of surface-based analysis with the surface extraction, which starts with this WF.mgc, dipping it in chocolate essentially to, or whatever this green stuff is, that glues itself to the outside of it. And now we can render this as an actual surface using a surface rendering program. And you can see with the and so this is where we get this LH.ridge from. And you can see that the ridge is actually very jagged because that surface is following these 1 millimeter boundaries. So it has these 1 millimeter jaggedness to it. And so this is a slide that Bruce already showed, but it's worth going over again in a little bit more detail. And that this jagged surface that we have here is called a surface model. And so one of the things that you should get out of this class is to understand what a surface is. Because if you've been doing neuroimaging for a while, but you've never dealt with surfaces, this is the new animal. And so you have to get comfortable with working with surfaces and understanding what surfaces are. So in this case, a surface is a mesh. And so where each mesh, the mesh is made up of these triangles. And so where these triangles meet is called a vertex. And each vertex has a neighborhood, meaning that it has some number of vertices that are connected with it. Each vertex has some XYZ coordinate. And those are the things that define what the surface model is. So a surface model has 3 aspects to it. It's a list of vertices, the nearest neighbors of those vertices, and the XYZ coordinates